I've used Excel to estimate a simple regression where the only right-hand side variable or the only independent variable included is the payment in log form. Now, Excel uses residual instead of error here, and I think that can be confusing. So what I like to do is I like to change it to error, estimated error. Residuals are estimated errors. And so the sum of squared errors is 7,758, where the sum of squares due to regression is 6. Now, the R square is a variable that kind of gives you a feel for how well the model has performed. And the way you interpret the R square is you memorize this sentence. R squared times 100% of the variability in Y can be explained by the model. What you're going to do is you're going to replace the R square with 0.001, and you're going to multiply it by 100, not 100%, but 100, and the result is a percentage. And you're going to replace the Y with what it is. In this context, Y is the employment population ratio. In simple regression, you look at and interpret the R square. In multiple regression, you interpret the adjusted R square. So the R square says what? Well, multiplying 0.001 times 100 gives you 0.1. So 0.1% of the variability in the employment population ratio of low-income single mothers can be explained by the model. So this model doesn't seem to work very well, does it? And it's because we're omitting a lot of information that is important. So it looks like we have an admitted variable bias issue, right? Look at the payment, for example. The higher the payment, the more women in this group are going to work. That is counter to our theory. So we got a wrong sign, and if you also notice, the p-value is very, very large. So with that large p-value, we can conclude that that coefficient there, 0.6087, is no different from 0 in a statistical sense. We could not reject the hypothesis that the true coefficient is 0. Now in this regression, we've included 5 more right-hand side variables. The dummy variable for the year 2000, the dummy variable for the full sanction policy, the share of the black population, the share that is a high school dropout, and the state's unemployment rate. I like to change, like I said before, the word residual to error, and then we want to interpret the adjusted R square. So we pull out that blurb again, we multiply the adjusted R square, which is 0.486, by 100, and we get 48.6% of the variability in the employment population ratio of low-income single mothers can be explained by the model. So that's a massive improvement from simple regression. And no model is going to have 100%. I mean, so usually anything around 50% or higher is usually a pretty good R square, adjusted R square. I've seen papers with adjusted R squares that are 30%. Now notice the coefficient on payment, log payment. It's now negative and quite large. At the same time, the p-value is less than 5%. It's 2.3%. So it looks like we've accounted for much of the admitted variable bias when you do a simple regression. Now let's form the predicted equation. Y hat, or the employment population ratio predicted, equals the intercept, the estimated intercept, minus the coefficient, estimated coefficient for payment, times natural log x1, minus 2.821 times x2, x2 being the dummy variable, the year 2000, plus 3.768 times x3, x3 being the dummy variable for full sanction policy, minus 0.29 times 91 times x4, and x4 being the share of a state's population that is black, minus 0.374 times x5 being the share of the state's population that's a dropout from high school, minus 3.023 times x6, with x6 being the state's unemployment rate. That's the predicted equation. Okay. Now, one of the first assumption of the model is that the expected value of the errors is 0. Now, that's probably true since the expected value of the estimated errors or predicted errors is 0. And I can show you that right here in this example. We have the predicted equation that we just formed from the previous slide across the top. And then we have the first observation. We have the first observation, second observation, third observation, fourth observation, yada, 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 all the way down to the 98th observation, the 99th observation, and the 100th observation. I can't show you them all, but I think you get the picture, right? So what we're going to do here is we're going to plug in this value into that variable there. We don't need to take the natural log of it because remember this is already in logs, right? This payment's already in logs. These are logged dollars. So we're going to plug this value into here. We're going to plug this value into x2. We're going to plug this value into x3. We're going to plug this value into x4. We're going to plug this value into x5. We're going to plug this value into x6, and we're going to hit equals. And when we do that, we get 43.83. Now notice that we observed 52.35% of women in this state are going to work that are in this cohort, right, of low-income single mothers. We predicted that 43.83% of those women would be employed. So the model's not perfect. It doesn't do a perfect job of predicting what we observe. Hence we have a residual. The residual is 8.52. Okay? Because the observed value minus what we predict, the difference is 8.52. So this value minus that value is 8.52. So our model underpredicts what we observe. Let's do it for the second observation. When we plug in these numbers into this equation, we get 40.76. Now the model here has predicted the second state in 1994 to have an employment population ratio of 40.76 when we only observed 38.47 in the state. So here the residual is negative 2.29. So the model has over predicted the employment population ratio. And notice that this prediction is a little closer than reality, a little closer to reality, what we observe. We do it for the third observation, the data, and we get 51.19. Again, this third state in 1994, the model over predicts what we actually observe, 49.69. And so the residual is negative 1.150. So far the model's done the best job at predicting the employment of low-income single mothers for this third observation. In the fourth observation, we get 39.60. Now that's a long ways away from truth. So far, it's the largest residual or estimated error of all of them that we've computed so far. And then yada, 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 all the way down to the 98th observation. So our model predicts employment population ratio to be 49.31% when we observe 51.1%. So the residual is 1.79, the difference in those two. We have the 99th and the 100th. So it looks like from the very limited sample of observations that we have 100 observations and we're only looking at 7 of them. So far, the 100th observation has the smallest predicted error in absolute value. Now, if I sum these, I'm going to get 0, and you do. You get 0. So we just verified assumption 1. The error probably has an expected value equal to 0 since the mean of the predicted residuals is 0. Now the next thing we have to check for is heteroskedasticity. And all heteroskedasticity means hetero is changing. Skedasticity is dispersion or variance. So we want to look to see if the variance is constant as a variable increases, as one of the right-hand side variables increase. So we have the residual here, 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 and here. Then we have the predicted value of y, or predicted EPR, y hat. We have the payment variable. We have the share of the population that's black. We have the dropout rate, and we have the unemployment rate. Now notice we don't have the dummy variables. Those scatter plots are rather uninteresting because the variable can only take on one of two values, 0 or 1. Now when we look at the residual versus the predicted employment population ratio, that looks pretty good. That's exactly what we want to look or see. Kind of a horizontal random band of points. This one's probably okay too. But look at this one. It kind of looks like there's a lot of variance for small values of the share of residents that are black versus a very large variance, or small variance, sorry. We have a large variance here for very small values of black, and we have a very small variance for states with a very large share of the black population. So this variable might present a problem. The dropout rate variable looks okay, and so too does the unemployment rate. So the only one that looks like it might be a problem variable is the share of the population that is black. Now a lot of that is because there's only one state with a share of the population that is black that's greater than 35%. Meanwhile, we have lots of states with the share nearly 0. To test for heteroskedasticity, we perform White's squared residual test by first squaring the residuals. So to do White's squared residual regression, we're going to square these residuals. We're going to square them. And when we square the residual, we're getting an estimate of the variance for that observation. And we want to know if that variance changes in the independent variables. So we're going to first square the residuals, and then we're going to use these as the new y in a secondary regression. Using the squared residuals as the new y variable in Excel, we come up with this set of regression results. We have payment, 2,000, full, black, dropout, and the unemployment rate. Those were all used when the y was the employment population ratio. Now that the y is the squared residual, we have them, plus we have payment squared, black squared, dropout squared, unemployment squared. Now we don't have full squared or 2,000 squared because remember, 0 times 0 is 0 and 1 times 1 is 1. So 2,000 squared would be perfectly correlated with 2,000. Full squared would be perfectly correlated with full. So that's why we don't include those. A software program is going to drop them anyway. And then we have the payment times the year 2000. We have payment times black. We have payment times dropout. We have payment times full. We have 2,000 times unemployment, full times black, full times dropout, full times unemployment, black times dropout, black times unemployment, and then dropout times unemployment. So we have all these squared versions of the variables and all the interacted combinations. Now this is the ANOVA table from this regression. If the f-stat, in this case 1.24, if the f-stat is smaller than the critical value, say we're using a 5% level of significance, we cannot reject the null hypothesis of homoskedasticity. Now the way you get the critical value is you first have to pick a significance level. We picked 0.05, and then you have to find it in the table. So you go to column 95 of an F table, and you go to row that corresponds to degrees of freedom equal to 74 and a significance level of 0.05. And so the intersection of this column with this row is 1.66. So the f-stat is less than the critical value. So we conclude that the variance is probably constant. So heteroskedasticity isn't a problem. Now, if heteroskedasticity is a problem, then we have some issues. Estimated coefficients aren't biased, but the coefficient standard errors are wrong. What does that mean? Well, if the standard errors are small, then your t-stat is going to be large. Because remember, the coefficient is going to change. Or maybe your standard errors are too big because of the heteroskedasticity. That's going to pull your t-stat down. So t-stat that should be significant may not be. In our example, heteroskedasticity does not seem to be a problem. If it is a problem, then you do what? You can compute Huber-White standard errors, or you can, if you know which variable is causing the problem, you can divide all the variables, including y. You can divide them all by the square root of that variable or some other form. But that changes, doing that changes the coefficient. So that's why a lot of economists don't use that approach. Typically they just use Huber-White standard errors, which are sometimes referred as robust standard errors. Now the values of the error term are probably independent if the autocorrelation residual plot or if the Durbin-Watson statistic indicate the values of E are independent. Now the Durbin-Watson stat, if it's equal to 2, we would conclude no autocorrelation. If the Durbin-Watson stat is equal to 4, then we have perfect negative correlation. If the Durbin-Watson stat is 0, we would conclude perfect positive autocorrelation. And what we want is something close to 2. The closer to 2, the better. Okay, now the Durbin-Watson stat varies when the data's order is altered. If there are multiple time periods, you want to compute the Durbin-Watson stat after sorting by time periods. If the data is cross-sectional, you may want to sort the data by some geography. Like, for example, put the states in the Northeast together, put the states in the Northwest together, yada, yada, yada. Some kind of geographic sorting. If the data is both, compute the Durbin-Watson stat after sorting by time period and geography. So the way typically a Durbin-Watson stat is computed for panel, or not panel data, but cross-sectional data. Now remember, this is kind of a panel data. I got 2 panels. I have 1994 and the year 2000. If you don't tell the software program that you have a panel data, it will compute the Durbin-Watson statistic incorrectly, like I'm going to show you here. If you tell the program that you have a panel data, you have a time variable, and you have an observational unit variable, a panel variable, like states, then it will know to compute the panel version of the Durbin-Watson. But this is how the Durbin-Watson will be computed for time series data. So the first thing you do is you take the difference in the residuals. So you subtract this. You subtract this from that, and you get 3.00. Or no, you get something and you square it, and you get 3.00. And then you subtract this from that, and you get something that's pretty close to 5 in absolute value. You square that, and you get something close to 25. So you take the difference in these two things, and you square them. Okay? And then you square the residuals after you sum the previous column. Ignoring this over here, if these residuals are ordered by time, and we had a time series model, like for example we had just the state of North Carolina over 15 years, this is how you calculate the Durbin-Watson statistic. So we're kind of computing the Durbin-Watson statistic in the incorrect way. So the Durbin-Watson statistic is basically just the sum of this column divided by that column, and you get 2.03. If you computed a Durbin-Watson statistic and you were using cross-sectional data, you're probably going to get something close to 2. So you don't really need to estimate or compute the Durbin-Watson stat if you're using cross-sectional data. If you're using a time series of data for a particular state, then this is what you do. If you wanted to include 50 states in a study over time, then you use the panel data version of the Durban-Watson statistic. So here there's no reason to doubt the assumption that errors are independent, and that's because we only have 2 years, and essentially our data set is cross-sectional. Now, if autocorrelation or serial correlation is a problem, estimated coefficients are biased, but their standard errors may be inflated. So you're going to have your standard errors are going to be larger than what they really are, which is going to mean that your t-stat is going to be smaller than what it should be. What that means is maybe the t-stat is 4, but because you have an autocorrelation problem, the standard error is quite large. Your t-stat ends up being, say, 1.5. So what should be a significant coefficient isn't. So hypothesis testing is unreliable. In our example, autocorrelation does not seem to be a problem because, like I said, we only had 2 years, so we don't got t's not very long, and we actually computed the Durban-Watson statistic incorrectly for illustrative purposes. Now, if autocorrelation is a problem, you do one of the following: you change the functional form, include an omitted variable, use generalized least squares. Or what most people do is just compute Newey-West standard errors. This is kind of like the Huber-White errors that you did for heteroskedasticity. When autocorrelation is a problem, you want to use Newey-West standard errors. Now, the true model is probably linear if the scatter plot of the residual versus the predicted value of y is a horizontal random band of points. And here we have the residual. I've already shown you this diagram. We have the residual versus the predicted value of the implement population ratio. And I fit a line, a curve, to this scatter plot, and it's flat. Now, if you fit a 2-degree polynomial to this scatter plot instead of using a linear scatter plot, and there is a substantial bow in it, then the model is probably not linear. Okay. You want the coefficients of this quadratic equation, you want both slope coefficients to be 0. So for example, you'd have the residual equal to some number, 0, plus 0 times y hat plus 0 times y hat squared. And you want the slopes and the intercept to be all 0. Okay, so if that's the case, the height of this quadratic equation is going to be 0, and there's no problem with the scatter plot. There's no pattern in the scatter plot. So then we would say, all right, it looks like linearity is all right. So we don't have a problem with the model being nonlinear. So we say, okay, we move on. Now, if you fit a linear model to data which are non-linearly related, the estimated coefficients are biased. So the coefficients have a problem now. The coefficients are biased. So the coefficient is larger than what it should be. So the t-stat is going to be larger than what it should be. Or the coefficient is smaller than what it should be, and the t-stat is going to be smaller than what it should be. So predictions are going to be seriously, there's going to be a problem with the predictions, which is going to make hypothesis testing difficult or problematic. In our example, nonlinearity does not seem to be a problem. The data are non-linearly related. Do one of the following: rethink the functional form, transform one or more of the variables, kind of like what we did with the payment variable. We took it from dollars to log dollars. Now we want to check for normality. The error is probably normally distributed if the residual is normally distributed. And this is a histogram of the residuals. I have what looks like 2 residuals that are between -16 and -12. 7 of the residuals look like they're between -12 and -8. 20 are between -8 and -4. 24 are between -4 and 0. 23 are between 0 and 4. 14 are between 4 and 8. 6 are between 8 and 12. it looks like 3 are between 12 and 16, and then 1 is between 16 and 20. Now, this looks normal, and you can plot it with a normal distribution curve, which I do here. And notice how close the height of this red curve is to this bar, right? The average height of this red curve would be about the same as the height of this bar. Same thing here, right? If I took the average height of this bar, I mean this graph, I'd get this bar. Now, what about in this? What about in this region? We don't have that luxury, do we? We have what? The average height of this red curve is probably down here. So the difference is quite large there. But then the relationship returns, right? The height of this red curve is approximately equal to the height of this bar. Yada, yada. Yada, yada. Yada, yada. But not here. Here, the average height of this bar is below the average height of this red curve is below this bar. And the same thing here. But other than that, I mean, that looks like a pretty good normal distribution. And when you're talking about real data, sometimes that's the best you get in terms of normality. There are a number of normality tests one can choose. We're going to use the Shakara-Bar test. It uses the skew of the residuals and the kurtosis of the residuals. The test statistic is chi-square with 2 degrees of freedom. You plug in the square of the, you square the skew, you add that to the kurtosis squared divided by 4. You multiply that sum by what would be 100 here, because we have 100 observations, and you divide that by 6. Now, kurtosis means the peakness of the probability distribution. High kurtosis means there's a very sharp peak. Low kurtosis means there's a flat peak. If you look here, I would say kurtosis is pretty mild, right? If this bar, and that bar were all the same height, then you'd have low kurtosis. If this bar were, say, way up here, and these bars were way down here, then you'd have large kurtosis. Kurtosis involves raising standardized residuals to the 4th power. Excel can compute the kurtosis. All you do is type equal kurt, parentheses, A1 to A100. A1 to A100 is where your residuals are located. And then you just hit enter, and what will show in that cell will be 0.0214. Skewness measures the symmetry of the distribution. Zero skew means the distribution is symmetric. Negative skew means we're skewed to the left. Positive skew means skew to the right. This is the center of the distribution, right? I have a little tail here and I got no tail here. I got no height here and a height of 1 here. I have a height of 2 here and a height of 3 here. I have a height of 7 here and a height of 6 here. Yada, 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 right? So I have a height here that approximately equals this height. So I would conclude that, so the skew is going to be really close to 0 in my opinion. Okay, the skew involves raising standard residuals to the 3rd power. Excel will compute it for you by typing equal skew, and then you put in parentheses where the residuals are located. You hit enter and you get 0.3276. You plug those two numbers into this equation plus 100 for the sample size, and you get a chi-square stat equal to 1.791. Now, if you remember back to your business statistics class, your advanced one, where you covered chi-square test, the degrees of freedom is the center or the hump of the distribution. So our degrees of freedom here is 2. So the hump is at roughly 2 because we have 2 degrees of freedom. Now, if we're using a significance level of 0.05, we're going to shade the upper tail red and label it 0.05. And our chi-square stat, or our chi-square critical value, our chi-square critical value is the chi-square value that gives us an upper probability value of 0.05. So we find that in the table. It's in column 0.05 of a chi-square distribution table and in row 2. So the probability that a chi-square value is greater than 5.99 is 0.05. Okay. Now our chi-square stat was 1.791, so we're really close to 0. Now the closer the chi-square stat is to 0, the closer it is to 0, the closer the histogram is to the normal distribution. So you want a chi-square stat that is close to 0. Hence, there is no reason to doubt the assumption that the errors are normally distributed. If the errors are normally distributed, parameter estimates are normally distributed, F and T significance tests are valid. If the errors are not normally distributed, but the sample size is large, which is beyond the scope of this course, parameter estimates are approximately normally distributed by the central limit theorem. F and T tests are valid. If the errors are not normally distributed and the sample size is small, parameter estimates are not normally distributed. F and T significance tests are not reliable. Now, since all 5 model assumptions appear to be valid, the T and F tests are going to be reliable, provided the right regressors are included. Given that the 5 assumptions of the error model seem to hold, we now move to significance testing. We have 2 sets of significance tests. We have the overall test of significance, the model fit, using the F statistic, and we have the individual T test for each individual coefficient. Notice in the null hypothesis we have beta 1 equal beta 2 equal beta 3 equal beta 4 equal beta 5 equal beta 6 equal 0. We don't include the intercept here. The intercept is beta 0. Why do we label it beta 0 and these beta 1 through beta 6? Well, beta 0 isn't multiplied by an x. Beta 1 is multiplied by x1. Beta 2 is multiplied by x2. Yada, yada, yada. Beta 6 is times x6. Okay, so we don't include the intercept in this test. Because remember what the intercept is. If the x's have no predictive power over the y variable, beta 0 would be equal to the mean of y. Now think about that. If the null is true, right, and we're regressing y versus all those x's and a column of 1s, and none of those x's have any predictive power whatsoever over y, then y regressed against a column of 1s would give you the sample mean of y. Now, because there are 6 slope coefficients for the 6 variables in this example, the degrees of freedom for the numerator of the f critical value is 6. Well, with 6 x's and 1 intercept, there are 7 parameters being estimated in the model. The intercept and the 6 slope parameters. 7 minus 100, we had 100 observations in the data. 7 minus 100 is 93. So the F critical value is found in the F distribution table in row 93 in column 0.05. The intersection of column 6 and the row corresponding to 93 and 05 is 2.20. Now, if you recall, if you go back to the regression output, the F statistic is 16.623. Since the F statistic, 16.623, is greater than 2.20, it is in the reject the null region. There is insufficient evidence to conclude that the coefficients are not all equal to 0 simultaneously. Given that we rejected the null hypothesis that all slope coefficients are equal to 0 simultaneously, meaning there's at least one not equal to 0, now we're going to test individual coefficients for significance. We're not going to test the intercept. We're going to test each of the individual coefficients. So the first one we're going to do is the one that corresponds to the payment, the log payment, x1. So we're going to test whether slope coefficient beta 1 is equal to 0. Now we're going to use a significance level of 0.05 like we have been doing. Because it's a two-tailed test, we divide the alpha by 2. And this tells us what column to go to in the t-table. And then we had 6 slopes, 1 intercept. Subtract 6 and 1 from 100, and you get the degrees of freedom for this test. And that takes you to row 93 in the t-table. Now, if you were in the t-table of a stats book, and you go to row 93 and column 0.025, you will see 1.986 in the intersection of that row and column. And because this is a two-tailed test and we have symmetry, the other critical value is negative 1.986. The probability of t being greater than 1.986 or less than negative 1.986 is 0.05. 0.025 plus 0.025. Now, if the t-stat is in this region here, we're going to conclude that, well, if the t-stat is in this region here, this gray region, if the t-stat is inside negative 1.986 and 1.986, we're going to conclude that the null hypothesis is true. Now, if the t-stat is out here, then we can conclude that beta 1 is positive. If the t-stat is down here, we're going to conclude that beta 1 is negative. Now, the t-stat, remember, was the coefficient divided by its standard error. And we got that from the table. Remember, the coefficient was negative 5.709, and its standard error was 2.61. The t-stat was a negative 2.320, and the p-value is 0.023. And that's exactly what we get here, negative 2.32, which means the t-stat is in the reject region. So we reject the null at a 5% level of significance, meaning TANF welfare payments influence the decision to work. The cool thing about doing individual significance tests is that the alpha doesn't change, the degrees of freedom don't change, and nor do the critical values change. So all we got to do is recompute the t-statistic. Now, the t-statistic for beta 2, if you recall, is negative 2.821 divided by 2.029 for a t-stat of equal to 1.390 and a p-value equal to 1.68. So negative 1.39 is in the do not reject region, meaning since the t-stat is in the reject region, it's close to 0. We conclude that beta 2 is probably 0. Hence, we cannot reject HO, the null, at a 5% level of significance, i.e. welfare reform in general does not influence the decision to work. Next, we move to the third coefficient. Again, alpha divided by 2, the degrees of freedom, the reject region, they don't change. The only thing that changes is the t-stat. Remember, the third coefficient belongs to the full sanction variable, and its coefficient was 3.768. Its standard error is 1.927. Divide the 2 and you get 1.955, and the p-value is 0.054. 1.96 again falls in the reject region, but notice how close it is in value to 1.986. Remember, the p-value of 1.96 is just above 0.05. Just above 0.05. So, although we cannot reject the null at a 5% level, we can at the 10% level because the p-value again was 0.054. 1.96 is really close to 1.986. Hence, I would conclude the full sanction policy influences the decision to work. The next coefficient, beta 4, its t-stat is B4 divided by B4's standard error. B4 corresponds to the share of the population that is black. And its coefficient, estimated coefficient, is negative 0.291. Standard error is 0.089. The t-stat is negative 3.256. And the p-value is 0.002. The p-value again is very, very small because in absolute value the t-stat is rather large. So we divide the estimated coefficient by its standard of error, and we get negative 3.26. Negative 3.26 is out in the left side rejection region, meaning we reject the null at a 5% level of significance. That means the share of the population that is black influences or is associated with more employment of low-income single mothers. Beta 5's t-stat is B5, its estimate, divided by its standard error. I'll not go back to the table this time. But its estimated coefficient is negative 0.374, and its standard error is 0.202. Hence, the t-stat is equal to negative 1.85, which puts it in the do not reject region. Since the t-stat is close to 0, we conclude that the null hypothesis is probably true. We say that we cannot reject the null at the 5% level of significance. Now, since 1.85 is kind of close to 1.986, its p-value is actually 0.068, which means although we cannot reject it at the 5% level, we can at the 10% level. So, using a 10% level of significance, the share of the population that is a high school dropout probably is associated with more work. The last and final coefficient belongs to the unemployment rate. The t-stat is B6 divided by its standard error. The coefficient was negative 3.023. B6's standard deviation was 0.618. The t-stat is negative 4.89. And so it is out in the negative part of the rejection region. So we're going to conclude or reject the null at the 5% level of significance, meaning the unemployment rate influences the decision to work. Now, we're going to interpret the coefficients. Once we determine which coefficients are no different than 0 in a statistical sense, we can then interpret the values of significant coefficients. And since B1 is statistically significant, we're going to interpret its value. And we do it as follows. Now remember, we took the log of x1. We took the log of it. So interpreting a coefficient whose variable is logged is much different than interpreting the coefficient of a variable that wasn't logged. So what we're going to do here is we're going to take y hat evaluated at x1 equal 292 and y hat evaluated at x1 equal 266. Now it doesn't really matter what the other x's are equal to, but if you want, plug in the means of x2, x3, x4, x5, x6. It won't matter because when we take this difference, those things all cancel each other out. Same thing goes with the intercept. The intercept minus intercept is 0. So it doesn't really matter what you do with the other things. Now why do we pick 266? Well, 266 is the average for x1. 292 is, I think, 10% greater than 266, if I remember right. So we have, now since this is x1, not log x1, but beta 1s, or the b1s, were computed using logs, we have to take the log of 292 and the log of 266. Now, everything else in the equation has been subtracted out, like I said. So what you're left with is, when you take this difference, are these two expressions. Now, when you take a difference of logs, that's like taking the log of the ratio. And so log 292 minus log 266 is equal to log 292 divided by 266. If you don't believe me, plug it into your calculator. Log of 292 minus log of 266 is equal to the log of 292 divided by 266. Now it just so happens that 292 divided by 266 is 1.1. So we're talking about a 10% increase in the TANF benefit for a family of 3. Okay. Now, the way this works is we're factoring out the B1, right? So B1 times, say, 4 minus B1 times 2 is the same thing as B1 times 4 minus 2. So that's what we're doing here. We're logging it, we're factoring out the B1. And B1 was just equal to minus 5.709. So minus 5.709 times the log of 1.1 is a negative 0.54. What does that mean? Well, increasing monthly benefit levels for a family of 3 by 10% would result in a 0.54 percentage point reduction in the average employment population ratio of low-income single mothers. So that agrees with our theory. Our theory said, you raise this benefit, you're going to get less work. Now, since B2 is insignificant at levels greater than 15%, its p-value was bigger than 15%, we interpret it as follows. Welfare reform in general had no effect on the employment population ratio of low-income single mothers. Since estimated coefficient B3 is significant, albeit at the 10% level, we interpret its value as follows. Now, remember what I said. When you don't log an x versus logging an x, you interpret the coefficients differently. So what we have here is, since x3 enters this equation linearly, whereas x1 didn't, x3 enters in linearly. Remember, what is a slope? What does B3 equal in mathematics? The rise over the run. The rise is a change in y, and the run is a change in x3. So what does B3 equal? It equaled 3.768 according to our regression output. Now that's kind of hard to interpret by itself, so what I do is I multiply the numerator by 1, and then I multiply the denominator by 1, or I put the whole thing over 1. Because 3.768 divided by 1 is 3.768. This makes it easier to interpret. So what this means is the employment population ratio of low-income single mothers is 3.78 or 68 percentage points higher in states that adopted full sanctions for families that failed to comply with work rules. Remember, x3 is a dummy variable. It's 0 if a state has no full sanction policy. It's 1 if it adopted a full sanction policy. So when you go from 0 to 1, x3 is increasing by 1. So when x3 goes from 0 to 1, a state is adopting a full sanction policy. And if they do that, the employment population ratio of low-income single mothers increases by 3.768 percentage points. Now, since estimated coefficient B4 is statistically significant at the 5% level, we interpret it as follows. Again, we're using the rise over the run because x4 enters the equation linearly. The change in y over the change in x, which is equal to b4, well, that we estimated that to be negative 0.291. Again, we put that over 1 because negative 2.91 divided by a plus 1 is negative 2.91. Now I'm going to multiply it by 10 because 10 divided by 10 times negative 0.291 divided by 1 is still negative 2.91. If you don't believe me, plug it into a calculator and you'll find out that what I'm saying is true. So now we have negative 2.91 divided by 10, which is still negative 0.291. That's much easier to interpret. So each 10 percentage point increase in the share of the black population in states is associated with a 2.91 percentage point decline in the employment population ratio of low-income single mothers. Now, since estimated coefficient B5 is statistically significant at the 10% level, we interpret it as follows. Again, x5 enters the equation linearly, so B5 is just the rise over the run. It was equal to negative 0.374. Putting that over 1, multiplying by 10 over 10, gives you negative 3.74 divided by 10, which is still negative 0.374. So this says each 10 percentage point increase in the high school dropout rate is associated with a 3.74 percentage point decline in the employment population ratio of low-income single mothers. Since estimated coefficient B6 is significant at the 5% level, we interpret it as follows. Again, the unemployment rate, X6, entered linearly, so it's the rise over the run. We estimated its coefficient at negative 3.023. Put that over 1 because 3.023 is quite large. We're not going to multiply this by 10 over 10. Well, I guess we will. Sorry. I apologize for that. So we have negative 30.23 divided by a plus 10. What does this say? Each 10 percentage point increase in the unemployment rate is associated with a 30.23 percentage point decline in the employment population ratio. Now, this multiplying by 10 over 10 is instructive. Sometimes it's appropriate and sometimes it's not. I would say here it's not appropriate because rarely are you going to see the unemployment rate go, say, from 5 to 15%. So maybe we should have used a ratio of 5 over 5 or 2 over 2 or just left it the way it was. If we left it the way it was, we would conclude that each 1 percentage point increase in the unemployment rate is associated with a 3.23 percentage point decline in the employment population ratio of low-income single mothers. So now that you understand how to build a testable hypothesis from theory and then collect data and then use that data to estimate a regression to test whether those hypotheses were correct or incorrect, now we can move into Chapter 2 and Chapter 3 and learn about labor supply and labor demand.